but a good one for last. So we have Eyke, and he is going to talk about uncertainty quantification in machine learning from Aleatoric to Epistemic. Please.
Okay, so thank you very much for the kind introduction and for inviting me here. It's a big pleasure to be here. It's also good to see that quite many people made it back after lunch to the to the last session. So my presentation is also about uncertainty quantification, yes, sure, with a specific focus on this distinction between what is often called aleatoric and epistemic uncertainty in the literature, which has received quite some attention, especially in the machine learning field in the last couple of years. So to set the stage, we are dealing here with a standard setting of supervised learning. So, and also to introduce some notation, we are given a set of training data, tuples xi, yi, which are typically assumed to be IID data coming from an underlying unknown joint probability measure P, a hypothesis space H given to the learner, which consists of a set of probabilistic predictors mapping from the instance space to the class of probability distributions over the outcome space Y, which here I assume to be finite and discrete, so we are basically in the classification setting, and a loss function that penalizes probabilistic predictions in light of observed outcomes Y. The task of the learner is to find a risk minimizing predictor H star, meaning a predictor which has minimal expected loss or minimal risk, where the risk is just defined as the expected loss, the expectation taken with respect to this unknown probability measure P. So the standard setting basically of supervised learning. Here is a simple illustration. The xi, the instances, you may think of X-ray images. The yi could be labels, in the simplest case, positive, negative, for example, depending on whether a certain disease is present or not. And then the task is to induce, to learn a predictive model, neural network, or whatever machine learning method you could think of, which then takes any new instance X as input and hopefully makes a good prediction for it. The prediction here is assumed to be a probability distribution. In the binary case, for example, the probability of positive, like 0.9. And such probabilistic predictions are, of course, good to have in safety-critical applications to give also an idea of how certain or uncertain the learner actually is in the prediction. So it's clearly better than just having a positive negative answer. Now the next question then is, of course, how much can we trust this 0.9 estimate? And in many talks before, I have heard about this problem of calibration and so on. So how well calibrated actually is that prediction? And it turns out that many machine learning methods are not very well calibrated, and in particular neural networks tend to be very much overconfident in some cases. So here is a simple example, a hand-picked example, admittedly. We trained a state-of-the-art neural network on such a fashion data set here. And then for these two cases, you get predictions umbrella and skirt, obviously miserably wrong, which is not actually the problem, because, of course, any predictive model can make mistakes. We as humans, we also make mistakes, not in these cases, but maybe in others. The problem here is that the neural network does not only predict incorrectly, but it at the same time reports a very high confidence. And this is not what we want. This is not what we call uncertainty aware. So we would prefer to have a predictive model that is uncertainty aware and actually notices when it's in a situation where it doesn't know enough to make a confident prediction. And this is exactly what does not happen here. Here is another example. We all know about this problem of hallucination in large language models, a question to the LLM, lowest temperature recorded in Antarctica, and the answer is wrong. Then the human user asks back how confident you are. I'm 100% confident. And again, this is not what we want. Yeah, we want that the system notices when it's in a situation where it's not really, where it shouldn't be actually certain. And the final example, this case of OOD data. Also, we heard yesterday already, and maybe even the days before, where I haven't been here, sorry for being late. I think Arno talked about this also, this problem. You train a predictive model on a certain data set, and then at prediction time during the application, the model sees new query instances which it has never seen before. For instance, you train an autonomous car on traffic signs, I don't know, in Germany, and then the car drives in another country and sees a new sign it has never seen before. And again, we would prefer if the model says, oh, I don't know, yeah, expresses a high degree of uncertainty instead of, I don't know, engaging in wild guessing and saying, this looks a bit similar to that one, so could be the same meaning. Yeah, this is what we definitely not want. And in this regard, this distinction between aleatoric and epistemic uncertainty is useful to make. I think it should be clear to all of you what this distinction refers to. By aleatoric uncertainty, we mean inherent randomness. This is a property of the data generating process, a property of nature, so to say, and as such, it is irreducible. The dependency between x's and y's, we assume, normally are non-deterministic, the ground truth. Epistemic uncertainty, on the other side, refers to the knowledge, the epistemic state of the agent, the learner in our case, and to a lack of knowledge of the agent, and as such, it is reducible in principle by collecting more information, more data, more whatever external information you can think of. And this distinction, arguably, is also relevant in a machine learning context, where, of course, the state of knowledge of the learner depends very much on the quantity and quality of the data it has seen so far. So, for instance, imagine we have seen a few data points, positive, negative, so every point could be an X-ray image, and then the learner is supposed to make a prediction here, and obviously the case is an uncertain case, not seen many data points so far, in the close proximity, almost nothing. So there is a good reason to be uncertain here. Here, the same point, the situation is different. It's again clear that this should be an uncertain point, but now the uncertainty in a sense is confirmed because the learner has seen lots of data and now it basically knows that it has a good reason to be uncertain and that probably it can't get rid of this uncertainty unless it changes the representation or whatever. And so this is somehow confirmed uncertainty, and we could say that this situation here is a bit more of an epistemic type, whereas this here is more of an aleatoric type. Of course, it's not only the data that plays an important role, important to mention, because it's often forgotten in the literature, and maybe not that relevant for neural networks, but if you think of other model classes, it's also, of course, the prior assumptions you start from. So here in this situation with the little data, if you make a strong assumption, for example, you assume that the two classes can be well separated by a simple linear model, then this might be enough to be relatively certain that this is a positive point, simply because all the models that match more or less with the data will say this is a positive point. Weakening the assumptions and, for example, also allowing for quadratic discriminant functions or whatever, makes this prediction again more uncertain, because now there are some, let's say, plausible models which say positive and others which say negative. Yeah. So of course, this interplay between what do you assume, what are your model assumptions, how does your hypothesis space look like, and the data. This is what plays together and eventually determines the certainty or uncertainty of the predictive model. So we may distinguish now different levels of what I would call uncertainty awareness. Here is an illustration by such a barycentric coordinate system. So this is a projection of the two simplex. Every point is a probability distribution over three different outcomes. So imagine, for example, you want to predict the outcome of a football match, win, loss, tie. And the ground truth, this is our assumption, is a probability distribution, a conditional probability distribution given X, where X in this example would be a football match. The least uncertainty aware predictor is of course a deterministic predictor, which just predicts one of the three corner points. A probabilistic predictor, this is basically the state of the art. My example from the beginning, you remember, you predict a probability, but the probability, even if you make an effort to calibrate it well, it will never really exactly hit the ground truth. So you will always deviate a little bit. And what I am now interested in is what I call a second order predictor, which is able to make more expressive predictions, which are able to reflect, to represent its uncertainty in the probabilistic prediction. And there are different ways in which such predictions could be represented. The Q here can be of different type. One natural choice would be again a probability distribution, which means that this learner here predicts a second order distribution, a probability distribution over probability distributions. Another choice, also not uncommon in the literature, is a creedal set, where you predict just a set of probability distributions. In the following, I will look at this case of a second order prediction, a second order probability distribution, which allows the learner to predict more or less spread or more or less concentrated distributions, yeah, where a very concentrated distribution would mean the learner suggests to be more certain, a more spread distribution, more uncertain. A simpler visualization, of course, is for the binary case, where the one simplex here is just the unit interval. You just predict, I don't know, win or loss. And then again, the ground truth might be some probability here. First order prediction, P hat, delivered by a first order predictive model H, a probabilistic predictor, a second order predictor capital H, this is my notation here, capital for second order, delivers a probability distribution over these probability distributions. Yeah? And again, the important point, this second order uncertainty here is in principle reducible. You can get rid of it by collecting more data or information. This uncertainty here you can't get rid of. You cannot move the P to 0 or 1 to the extremes.
So a hyperparameter is a special case, like where normally you always have like some sort of hyperparameters in your statistical model maybe, in your class of probability distributions. And you could say just the simplest case is I have a uniform over the hyperparameters or something else, or some other distribution.
Yeah. Yeah,
because that's the first thing that came to my mind when you were distinguishing between aleatoric and epistemic. Yeah. Where do hyperparameters fall? Hyperparameters fall somewhere in the middle.
Yeah, exactly. And you will see an example very soon where I use a Dirichlet distribution as a, so to say, conjugate prior over the binomial. Exactly. Yeah. Okay, so now, yeah, the question is how can we come to such second order predictors, yeah, practically? One way to go, of course, yeah, okay, no, just let me repeat what we want. Now we are interested in learning predictive model that delivers this type of second order predictions here, which I call capital Q, delivered by a second order predictor capital H, which adequately represent the learner's epistemic uncertainty. And now the interesting question is, of course, what do I mean by adequately? I will come back to this in a minute. Yeah, quite a number of methods have been considered recently in the literature. I can't, of course, give an overview here of all of them. A few words I will say on the Bayesian approach, which is perhaps the first that comes to your mind, and which is indeed one way to go. And then I will speak a little bit more about this idea of generalized loss minimization, on which we recently obtained some interesting theoretical results, which I would like to share with you. So yeah, of course, you could go the Bayesian way. Bayesians, in principle, are exactly doing this. Yeah. So if your hypothesis space is a space of probabilistic predictors, like neural networks, for example, with a softmax activation in the end or whatever, then every point here would be a neural network, for example. And then learning means turning your prior here into a posterior. And then when you want to make a prediction, you compute the posterior predictive distribution, which is just the image of that distribution of the posterior under the mapping here dictated by your predictor. And this is a second order distribution, which is exactly what we want. Yeah. So this is a distribution on the epistemic level. And of course, what typically happens in the Bayesian approach, the more data the learner has seen, the more peaked this second order distribution will become. So that's all fine. So basically what we want. Of course, we know on the other side that the Bayesian approach does have some difficulties. Yesterday we had some very interesting talks also. For example, showing that under model misspecification, the Bayesian approach will also be overconfident and so on. Apart from that, another drawback of the Bayesian approach is, of course, the computational complexity. Yeah. So what people recently have been working on, also something we heard already in previous talks, is Bayesian neural networks, where instead of having numerical weights, which you typically have in a neural network, and then a numerical output, you now put distributions on the edges as weights, so to say, probabilistic weights, and you get a distribution as an output in the end. And this is, again, a second order distribution. So this is one way to realize, in a sense, this Bayesian approach. Methods like dropout, job connect, and so on, you can also interpret from this perspective, and they also have been quite popular in the recent past. But yes, inference is expensive, and you have to do, I don't know, you have to use sampling techniques, variational inference, Laplace approximation, and so on, because exact computation is normally intractable. Ensemble methods are also used a lot these days, can also be seen under this Bayesian spirit, ensemble of deep neural networks, for example, with the idea, or at least the hope, that this is a somehow good discrete approximation of your posterior, which is theoretically a bit debatable, but still it's used in that spirit, and intuitively it does make sense. The idea is that you collect the predictions of the different ensemble members, and if they all agree, basically, then this is indicating a low level of epistemic uncertainty. If they all disagree very much, this is somehow suggesting a higher degree of epistemic uncertainty. This is the idea, roughly. Okay, good. So I would now This is actually the main part of my presentation. Speak a little bit more about this idea of second-order loss minimization, which recently has become also quite popular in the machine learning field. So what is the idea? The idea, you can motivate in different ways. We just talked about the Bayesian approach. Now you could say Bayesian methods are so expensive computationally. Can't we predict somehow, can't we train a second-order predictive model in a more efficient way, and maybe not do this detour via turning a prior into a posterior and so on? Can't we maybe just do the standard thing that we typically do in machine learning and do risk minimization? Yeah, train a predictive model by risk minimization. So can't we perhaps train a neural network or whatever model you could think of, which takes an X as an input and then produces directly a second-order distribution as an output, as a prediction? Of course, the second-order distribution you have to somehow parameterize because it's an infinite dimensional object. In the case of binary classification, let's take that simple example. You could, for example, parameterize your second-order distribution by a Dirichlet distribution, which in this case has only two parameters, alpha 1, alpha 2. And by choosing these parameters appropriately, you can predict different second-order distributions. 1, 1 is the uniform, suggesting high epistemic uncertainty. The higher the alphas, the more peaked, the more concentrated you make the distribution, the more different alpha 1, alpha 2, the more skewed. Yeah, so you could play with these parameters to obtain a meaningful second-order distribution. So this is the idea. But the interesting question now, of course, is can we train a model delivering meaningful parameters, alpha 1, alpha 2? So let us formalize the problem a little bit. Given training data, again, standard training data as we assumed before, xi, yi. The question is, can we train a second-order predictor, H, capital H, mapping from the instance space into this, the space of second-order distributions using simple empirical risk minimization? Yeah, what we typically do in machine learning. We have a loss function which I call LE here. E stands for epistemic because this loss function compares second-order predictions with outcomes, yi. We train a predictive model by minimizing the loss on the training data, the second-order loss, the epistemic loss, with a suitable second-order epistemic, if you want, loss function LE, which takes the second-order prediction and an outcome, compares the two, and delivers a loss, a real-valued loss as an outcome, such that the epistemic uncertainty of a learner is somehow represented in a faithful way. Yeah, and again, the question now is, what do we mean by faithful? So intuitively, one thing we would expect, of course, is that in the beginning, when the learner has seen very few training examples or no examples, the distribution, the second-order distribution will be flat, uniform maybe. And then it will, the more data the learner sees, the more concentrated the distribution will become around the ground truth, ideally the ground truth. And in the limit, when n goes to infinity, ideally the second-order prediction should converge to a first-order prediction where you put all the probability mass on the ground truth. Qualitatively, at least, this is what we would expect. Yeah. So this approach, actually, this whole idea, in a sense, it has a good motivation, I would say, because we know that at least the same thing can be done for first-order predictions. And we heard a lot about these proper scoring rules already. So we know that if we want to train a first-order predictive model, which just predicts probability distributions, first-order probability distributions, we can do that by empirical risk minimization if we take a good loss function, namely a strictly proper scoring rule. The LA here, A stands for aleatoric, because it's working on the aleatoric level. It compares a first-order distribution with an observed outcome. If we take a strictly proper scoring rule for LA, then we know we provide exactly the right incentive to the learner to predict the ground truth probabilities. Yeah, so for first-order distributions, we know it works, at least in theory. I mean, in practice, we know that often the predictions are still biased and not well calibrated, but theoretically, at least it works. And yes, sure, I don't need to explain you what strictly proper scoring rule is, but just to remind me, because I will generalize this on the next slide or so. LA is a strictly proper scoring rule if the expected loss, when we know that the outcome Y is sampled according to a distribution P, then the expected loss, the score, is minimized by predicting P hat equal to P. So any deviation P hat not equal to P will only increase the expected loss according to this loss function LA. Good. So the idea is well motivated. However, we recently obtained some interesting negative results showing that although it's done in the literature and although people also report good empirical results, the whole approach, the whole idea is really theoretically flawed. First, we showed that this idea actually cannot really work in a proper way for a specific class of epistemic loss functions LE, which are defined in this way. So you take the expectation of a first-order loss LA, typically a proper scoring rule, with respect to your second-order prediction Q. So basically, the idea is to take a first-order loss and then to lift it to the second level by taking expectation with respect to your second-order distribution. Yeah? But then in a follow-up work, we also generalized this and we showed that there actually cannot exist any second-order loss which incentivizes the learner to make really meaningful second-order predictions. And now again, the question you may wonder, what do you mean by meaningful second-order predictions and incentivizing? And I will show you on the next slide what I exactly mean. In practice, as I said, there are many papers. Which present good empirical results. However, they are, so I don't want to say they are cheating, but they are not using exactly this type of loss function here. But what they are doing, this is typically called evidential deep learning. This whole approach is typically called evidential deep learning. It has been introduced under this name a couple of years before. And they define the loss LE by adding to this original definition here a regularization term, which is typically the KL divergence of your prediction from a reference prediction, which is often the uniform distribution. And of course, this is obvious by adding this penalty here and multiplying with the regularization parameter lambda, you incentivize the learner to express epistemic uncertainty, yeah, to be close to the uniform. And the higher the lambda, the higher the incentive to report epistemic uncertainty. And this is, of course, not really what we want, because then it basically means that you externally control the level of epistemic uncertainty represented or predicted by your learner. By playing with a lambda, you externally control it. On the other side, there is of course the question, can we do better? Because it's true that by definition, epistemic uncertainty is not a property of the data generating process, but a property of the learner, the learning agent. And as seen from this point of view, it's maybe clear that we cannot expect to have an epistemic uncertainty prediction that is purely objective and purely coming from the data. Yeah.
And I again ask, I think this question is not just to you, but to all people. I'm new to this scoring stuff. So I mean, for me, you're bringing up a point now, which is not only on the second order, but on the first order loss function. Typically, one has to add regularization. And typically, there's lambda in the regularization term, in the loss term, is very much a tweaking parameter that depends on the stability of the forward process. So like, I mean, if I have an inverse problem where I have a very bad continuity of my operator, where the operator is not continuous, I need to put a lot of regularization. If I have a continuous operator, I have to put little. So I don't understand your comment that the epistemic uncertainty comes only from the data. It comes from the data generating process, in my opinion.
What I wanted to say.
Problem, I have more epistemic uncertainty. If I have a well-posed problem, I have less.
Yeah, my point was that the level, the degree of epistemic uncertainty is not only a property of the data, but also depends on how much you regularize this loss. And but I also said this is in a sense natural. In the Bayesian approach, you have the same. Yeah, the uncertainty, the epistemic uncertainty depends on how you specify your prior. But there, at least, you do it in a very explicit way. And you make it explicit. Here, it is a little bit coming implicitly, yeah, and not made very explicit. This is what I wanted to say. Okay, I will come back to this in a minute. Now, to make this a bit more rigorous, this point that we cannot, that there is no loss, no epistemic loss, no second-order loss, which incentivizes the learner to deliver meaningful second-order predictions. To make this a little bit more rigorous, what we did is we generalized this notion of a scoring rule, proper scoring rule, to a proper second-order scoring rule. Yeah, and this is basically done by generalizing this inequality that we have seen before to a double expectation, where we first sample, so to say, a first-order distribution from the second-order distribution, and then an outcome from the first-order distribution, and then we compute the loss. So imagine, for example, that the learner knows or believes that this that the second-order distribution is capital Q, and that the data is generated in this way. Then we would expect this inequality here. So the expected loss of any Q hat that deviates from the true or assumed second-order distribution Q should only increase the expected loss. So we should have this inequality as we had before for standard strictly proper scoring rules. So in other words, if the learner holds a second-order belief Q and it knows that it's penalized according to the loss LE, then it should report Q hat equal to Q and nothing else. And the question is, can we at least find a loss function LE which incentivizes the learner to predict what it believes? And the answer is no, we can't. This is what we have shown. You can't. You can't find such a loss LE that incentivizes the learner to predict what it believes. Here is what the learner eventually predicts depends on mathematical properties of the loss. But for the common case where the loss is the loss function, the first order loss LA is convex. So this is one special case where you can make a more concrete statement about what will happen and in which way the learner will deviate from the Q it believes, so to say. If the first order loss is a convex loss, log loss, prior score, what you want, and you lift it to the second order level by taking expectation with respect to Q, and you have a rich hypothesis space which has a universal approximation property like deep neural networks and so on, then you can show that the minimizer of this second order empirical risk, when you do not regularize, so you set lambda equal to 0, so this part here cancels out, the minimizer is a Dirac measure which is put on a first order distribution. And this means that the learner is incentivized to suggest that it has zero epistemic uncertainty, no epistemic uncertainty at all, yeah, for convex losses. If the loss is of different nature, it's doing something different, but the important point is it never really does what it's supposed to be, namely to report the Q, the capital Q it actually believes. Yeah, and as I said, if you want to avoid this degeneration, then you can do this by regularizing the first order loss. But yeah, this is a bit questionable whether this is actually what we want. Okay, so quickly one other result on a slightly different method, which so here you remember here we lift a first order loss to a second order loss by taking an expectation, and the expectation is outside the loss. There has been an alternative proposal in the literature where you take the expectation inside, so you move it inside the first order loss. Yeah, you have a second order prediction h of xi, and then you take the expectation here inside, and then you apply the standard first order loss to penalize. And this probably also looks a bit weird, because by taking the expectation here, we remove basically all information about the epistemic uncertainty, because we reduce again, in a sense, to a first order distribution. Yes, and this is exactly what happens. So what you do here is that first and second order spaces are now somehow combined into a single new hypothesis space, because every second order distribution capital Q gives rise to a first order predictive distribution PQ, if you want, by taking this expectation here, which comes from a space of first order distributions P bar, yeah, via this mapping here. And then the question is, do we gain anything? Or, also, can we expect that the learner in this way will be able to learn meaningful second order predictions? And you can answer this question by looking at how this space P bar actually looks like when you start from a certain space of first order distributions P. So in the case of classification, for example, what you typically look at is you have a categorical space of categorical distributions as your space P, on which you put a Dirichlet as a prior. And this combination here leads to, again, categorical. So you remain in the same space, and do not gain anything. But what is more important here is that this mapping here from the second order distribution Q to the associated first order distribution PQ via this expectation is not injective. And why is this maybe a problem? It's a problem because it means you cannot again identify the second order prediction because you minimize on the first order level and you can't identify anymore. So what you end up is more or less arbitrary again. In the case of regression, yeah, of course, often the normal distribution is taken as first order. You put, for example, a normal inverse gamma as prior, and then you will end up, the P bar here will be students' distributions. So you gain a little bit in expressivity, but again, there is no mapping is no injection. And again, you have the same problem of ambiguity. Counting data, you can also look at Poisson distribution, for example. Put gamma on top, you end up with negative binomial. Again, you are a little bit more expressive. Here it's indeed an injection, interestingly, that you obtain. But here there are other technical problems which again are a little bit troublesome. This is again summarized here. This is what I already explained. And especially the first two cases, due to this property that we don't have an injection, are again troublesome from the perspective of second order prediction, because it means that your second order prediction is again largely arbitrary. Yeah. So there is no unique risk minimizer on the second level, on the level of second order predictors. Okay, good. So, yeah, we also did some experimental studies in order to confirm these theoretical findings, and this is not very well visible here. Okay, I also don't think it's, I need to go into very much detail here. What you see is that what we did here is we took, this is hard to see, this green, this green curve here, this sinusoidal curve here. This is the ground truth parameter of a binomial distribution. So for every x here on the x-axis, we assume that the ground truth is a binomial distribution from which we can sample positive, negative. Yeah? And the function here, the green function, determines the Bernoulli parameter. So we sample from this, but only in the first half of the interval. So we simulate an OOD scenario where on the right, the learner hasn't seen anything. And what you see here, the first two cases are for outer loss minimization, the second two are for inner. And what you see here is that the extrapolation is relatively poor, as one can expect. But more importantly, the uncertainty quantification is even worse. So for lambda equals 0, no regularization. You see what I said before, the learner converges to a Dirac distribution, so suggests there is no epistemic uncertainty at all. If you regularize a bit, then the uncertainty gets higher, but still it's even lower on the right than on the left, which is again a bit weird and not what you expect. And it's also not covering the true function in any way. And the same for inner expectation, you have similar problems. So the whole approach is really a little bit debatable. So yeah, sorry for only showing negative results today, but I think this is also interesting from a mathematical perspective, and of course also important to gain insight and learn something about what works and what does not work. I mean, this is also often to understand why things don't work, or at least in theory cannot really work well. So to conclude, Yeah, I think this audience doesn't need to be convinced of the need to train uncertainty-aware methods, predictive models in machine learning, especially because nowadays machine learning is used in so many safety-critical applications. Although we had this discussion this morning, this interesting discussion of how people really appreciate also in practice and in industry and so on, this uncertainty quantification. This distinction between aleatoric and epistemic uncertainty, I think, is also important and well motivated. But maybe, yeah, this is what you have probably also seen from my presentation today, is that tackling the epistemic part is specifically difficult. So it's not easy to train predictive models which somehow report epistemic uncertainty in a meaningful way. In particular, I focus today on this idea of second-order loss minimization, which, as I said, in the literature is known under this notion of evidential deep learning, which, by the way, is also somehow a misnomer, because it's not really evidential in the sense of this Dempsey-Schaeffer theory of evidence. There is a couple of people who are quite upset about this name. But now it's too late, you know, when such a name has been given, it's hard to change. This approach, although it has attracted really quite a lot of attention in the recent past. I mean, this is also why we had a closer look at it. It's not just that there is just 1-2 papers. No, this is quite a lot of literature meanwhile, including whole survey articles about this idea of evidential deep learning. I criticize this this regularization where implicitly then you make the learner somehow not deteriorate to a Dirac, but to represent some epistemic uncertainty. I said this is a bit cheating, but yes, on the other side, it's clear that that epistemic uncertainty can't be just a property of the data, can't be fully objective. And what I find also quite interesting is to think a little bit about how this whole idea of evidential deep learning connects to standard Bayesian, to the standard Bayesian approach, because we know that standard Bayesian inference can also be connected to regularized machine learning, where the regularizer plays the role of the prior distribution. And but one important difference is that in the Bayesian approach, regularization is applied on the global level, is applied to the entire predictive model. Here in this evidential deep learning, you regularize every individual prediction. So regularization is applied on very different levels. Still, I believe that there is a connection between the two. And my conjecture is somehow that you can show that eventually eventually you can interpret this evidential deep learning method as a non-proper Bayesian learning approach, where you have the problem that the influence of the regularizer, which is the prior in Bayesian machine learning, does not diminish in the course of time. When you observe more and more data, the influence of the prior in Bayesian learning gets lower and lower, and here it remains always the same, because you put another prior on every new observation. Yeah? So this is a little bit what we are currently also looking at. Okay, with this, I thank you very much. These are the main references. These 3 papers contain these negative results I was speaking about today. And here is a couple of other references which I also recommend to maybe have a look at. And with this, again, thank you very much for your attention, and I'm very open to questions till 3 p.m. because then I have to catch my
have a little bit of time. Yes.
So to be sure that I understood your arguments, is it true that the problem with the second order loss minimization is that it always interpolates between on the level of the first order prediction, which is why then the losses can be arbitrary as long as the loss state is convex? Or
I'm not exactly sure what you mean with interpolation, but one key problem indeed is that you never this is, let's say, one of the formal reasons for which this whole approach cannot work, and which is also part of the formal proof that it can't work, is that you never observe data on the first order. So you never observe, together with an X, a ground truth first order probability distribution. What you only observe is an outcome of that distribution. So there is a gap in a sense, yeah? You only observe zero level, you only make zero level observations, but you want to you want to predict a second order distribution. And there is an ambiguity in between, so to say. Normally, there are many first order distributions which you can put in between and which explain the same, say, in the same way the outcomes that you observe. And then the question, which of these many first order distributions in between does the learner prefer, only depends on mathematical properties of your loss. And for example, if you have a convex loss, which is commonly the case, then you have this degeneration to a Dirac, etc. So yeah, this is mathematically the main problem. Would you have the opportunity to collect also first order distributions in your training data, then the whole problem would be gone. Yeah? Then you would basically have a standard learning problem again. But this is normally not what we have. So it's rarely, almost never the case that you make complete probability distributions, ground truth probabilities as observations.
Thank you very much for your talk. The problem you encounter with the expected, well, with the inception, reminded me of a simpler problem in the construction of the CRPS. So in the CRPS, you base on the absolute distance. And there is a representation where you say, taking expectation of the absolute value of y minus the observation. And then you correct it. Mm-hmm. And the correction is minus 1/2 of expectation of the difference between two replicates, mm-hmm. absolute value, which is the thing that makes the score proper. Mm-hmm. So it's a penalty on diversity. So did you consider something like that instead of the KL?
No. We did not so far, but it's a very interesting remark. I have to admit I'm not that familiar with this, but this was also part of one of the previous presentations today, right?
Yes.
Yeah. Yeah. I noticed this, but I have to admit, no, we never looked into this, but we will do.
Yes.
So thank you for the pointer.
And we have a question.
That's a good suggestion.
I don't think Jeremiah is here, but what he was talking about, like some of the slides you had, where you have expected value with respect to P, with respect to Q, plus the Kohlberg tablet, it's exactly what he was calling the post-Bayes approach. So if L was the log likelihood, lambda 1, you get exact posterior distribution in different loss functions. So it sounds like in that case you would get exact posterior, right? So you're sort of getting.
Yeah.
So what you're getting is what they are getting pretty much exactly, or is that not the case?
Yes or no? Yes and no. Yes or no is of course true. Yeah. No, good point. I mean, I was also attending this presentation yesterday and found it extremely interesting. But again, correct me if this is wrong, but I think the key difference is that his regularizer is again on the global level. So you do standard Bayesian learning, and you put a regularizer on the model, and not on every individual prediction, which is what EDL is doing, evidential deep learning is doing. So yes, I had the same at first sight when I saw the slides. I thought, wow, this looks very similar. But yes, I think the difference is on which level do you apply this regularization, and this makes an important difference.
So if you use the priors and mixtures, I might be able to talk about at some point.
Yeah, maybe.
Also, sort of connecting this work to Bayesian methods, I wonder if you've seen the work on embedded error models, because it sort of reminds me of what you're describing, where this will assume some density on each of the Bayesian parameters and just attempt to learn the hyperparameters from the data. And you do have sort of an effect where you can add more and more data and never learn anything.
So this goes into this direction of hierarchical Bayes?
It's a lot like hierarchical Bayes, but you don't try to learn a joint distribution on the parameters as well as hyperparameters, just the distribution on the hyperparameters.
Okay, once again, I have to admit, we didn't look into this so far, but it's again another very interesting pointer. So we'll have a look. Again, thank you very much.
Thank you for this super interesting talk. I should say I'm not really surprised about the negative results. Like intuitively, why should we expect models to become uncertainty aware, right? I would think that this uncertainty awareness should come from the data. And so if you're just inputting, yes or no, disease, no disease, data to train your models, then I just find it very, like, it would be extraordinary, really, to, get a model that is uncertainty aware. So, what people are currently doing is they're training on basically all the data that exists. LLMs, right?
You mean foundation models?
I mean foundation models. Yeah. And actually, if you look at uncertainty awareness of those models, they're actually pretty uncertainty aware. But the key is that those models are trained on the appropriate data sets. More importantly, actually post-trained on very relevant data sets where you have very high quality human annotation saying, hey, this is wrong, or like, I don't know, or like, this is ambiguous, and so on. And if you look at O3, right, like the state-of-the-art reasoning model of OpenAI, it has scaringly good calibration. I mean, I didn't believe that was possible, but apparently it is. So my claim is that we just need to focus on the data as opposed to kind of, I don't know, fiddling with losses but like, I mean, that's a hot take.
I would agree that maybe at second sight, this result is not so not so surprising after all. These foundation models, yes, you are right. They have somehow surprising capabilities, caring capabilities sometimes. But on the other side, with this uncertainty awareness, yes and no. I mean, I have given this example from the LMM in the beginning,
That's an old model.
And there are maybe an old model. Yeah, they are getting better, but hallucination is still an issue, right? And also the data they are trained on. Yes, it's way larger data, but still it's standard data. So yeah, it's still zero-level data. So, or do they have access to
I just think that
first-order data?
From human annotation, you are getting the ambiguity in various queries, right? I think a human annotation.
Yeah, but in principle, you could have the same ambiguity in your data as well. I mean, if you have X-ray images and some doctors. Yeah, but the humans, are they giving probabilistic labels then?
I mean, I guess they're expressing uncertainty, like, I'm not sure, like, this is ambiguous or something.
But this is rare data. I mean, this is valuable data to have.
Yeah.
But the foundation models are typically at least not only trained on this data. But I do agree that the data is playing an important role. And it's very clear, and this is also what I said before, if we would have access to first-order data, that would be very helpful for epistemic uncertainty quantification for sure.
Okay, we have to stop, unfortunately. Okay. Thank you for the discussion, and let's thank our speakers.